Hello, everyone. This is a talk that I gave at the University of Chicago's Data Science Institute, thanks to a really generous invitation from the Schmidt Fellows there, around my ideas on how my approach to computational science has changed, not only as my understanding of how to use artificial intelligence has changed, but also as the capabilities for it have dramatically improved over just the 10 years that I've been working in this area. So the presentation here will cover kind of ideas that range from the different ways that we can use machine learning better or the different ways we could think about computational science to do it differently. So before I get into kind of what my changes in opinions have been, I thought it'd be first to describe a little bit about where my experience has come from. And one thing that has really influenced my perspective on how to use AI in computational science is the opportunity that I've been given to work in many different areas of materials and other types of scientific modeling since I joined Argonne National Laboratory about 5 years ago. So what you're seeing here is just a quick summary of what I do as a staff scientist there, which the overall theme is variety. I worked as part of the exascale computing project while it ran. It ended this past December on how to integrate AI into different types of computational modeling. In particular, that focused on the design of molecules as part of the J. Caesar program, which also ended in 2023. And more recently, I've been able to study kind of ways of approaching using AI in experimental science through integrating computer vision into the study of how radiation damage affects material, and even more recently on how to use AI to increase the speed at which we can model battery degradation or increase the fidelity and reliability of models used to explain chemical separation processes. So with all of these sort of context in mind, I've been able to really see the different ways that computation is used and that we can change it with a varying perspective on ways that artificial intelligence can be employed. So really the overall tone of the presentation you're going to see today are many different facets and vignettes into computational science. And sort of stated simply, I'm being very reductionist here, are three kind of core ideas that I want to talk through today on policies or ways of thinking that I had when I started in graduate school, which was only about 10 years ago, and how I now think differently thanks to my growing experience. So we're going to cover things like how can I use artificial intelligence to reduce the amount of computation that I do, or which questions I ask, to how can I change the individual algorithms that I employ. So I'm going to cover these topics in sort of great detail. Hopefully we'll interleave through why I think AI can change these concepts. And we're going to, since this is a talk covering work that I've done, we are going to focus specifically on advancements that I've been around or been developing at Argonne that help change these ideas. So with that said, let's start out with the first one, which was the idea, particularly popular in the kind of early 2010s, that when in doubt, run as many calculations as possible, where the way that I'm hopefully going to argue today is that whenever we have a question where there's far more computations to run than are generally practical, that is the prime opportunity for using AI to help accelerate that kind of challenge. Now, to put that in specific terms, let's talk about something, and actually a slide from my candidacy exam during my PhD in 2013, just over 10 years ago. I defended my candidacy in December of 2013. So what we're seeing here is results from a paper that my colleague Scott Kirkland was working on at the time, where they had gone through a major effort to compute the properties of 180,000 possible combinations of different elements in a certain kind of material. Now, this was immensely useful. It allowed us to identify many materials that could be useful for, say, thermoelectrics or for strengthening precipitates and metal alloys, but it came at a significant cost. And a lot of that cost we could have avoided had we engage some more intelligence during our search. That red box, which I included in my candidacy exam, shows that of these 180,000 materials we evaluated, roughly half of them are so unstable that our odds of being able to make them, find them on the planet, or perhaps even find them in the universe is diminishingly small. Yet, for each of these materials, we spent on the order of 5 hours on a computer processor, which, if our cluster at Northwestern was powered entirely by coal, would be about 500 grams of coal being used to create this calculation. Now, the point here is that even though we could do these calculations, this need to be able to do all of them to derive some confidence that we found the optimal solution is something that was becoming obsolete in the early 2010s and should be something that is done very sparingly now. And the idea behind of where AI fits into this is that you can use AI to help you decide which calculations are the most valuable to run. The term that I prefer to use for this and see most in the papers I read is active learning. You may have heard it under many other names such as Bayesian optimization or optimal experimental design. But in all cases, the pattern follows this figure from the left, that by taking a machine learning model, training it on the data that you've acquired already, and using that to pick your next calculation, you can create a technique that can help you find which calculations or which data is most valuable to acquire to solve a problem. And you can use that whether your problem is to train a physics model, given the least amount of data, and some of my colleagues at Brookhaven have had some major success there, or you could use it to find, say, a point that optimizes certain properties. The picture on the bottom left shows some work on showing how you can speed up the discovery of certain materials by orders of magnitude using this kind of iterative approach. And given the prevalence of this kind of idea, I think it's very possible to do these kind of searches more broadly within computational science, because we have many of the tools that we need already to engage to make these kind of artificial intelligence driven processes common. There are numerous physics codes on one end. There are plenty of workflow engines to be able to automate running and processing the results of those physics calculations. On the other end, we have plenty of AI toolkits nowadays that can work with a variety of types of physics data in order to be able to predict the outcome of that calculation and thereby give you the raw ingredients that are needed to do some active learning. What the area that I've been studying, particularly during my time at Argonne, is what goes in the middle between these two. That is, how can we take the artificial intelligence tools and being able to tie them effectively to those computational workflows? And this is a problem that has some subtlety to it. And particularly once you start talking about using the major types of computational resources, such as supercomputers, which are available to many scientists. And the core problem in these is that the physics codes that we're running rarely need to be run at a scale that takes up the entire supercomputer. So instead of running one calculation at a time, people tend to run batches of them, or many concurrently, in order to gather data fast enough to solve a problem. And once you have that parallelism, many different strategies for how to tie AI into that workflow are possible. You could have on one end a purely batch-driven search where you wait to make that next decision about what to run until all the decisions that you've made earlier have been evaluated. And this is great. It means you can operate knowing that there are no ongoing calculations, you have all the data available to you. Yet if your calculations vary in how long they take to complete, you could get underutilization on the supercomputer, which is something that we strive hard to avoid. On the other end of the spectrum, you could keep a running list of tasks and update them asynchronously, which achieves utilization, but you're making suboptimal decisions because you're not running the best calculation possible at each point, because you're not waiting to evaluate the effect of the latest result coming in. So with all of this in mind, really what we've tried to study around Argonne is how can we integrate not just these three strategies, but the variety that are possible when you know a lot about the type of calculation you're seeking to run and what kind of computing resources you have available. So in short, these might not be the only three answers. Scientists can certainly come up with more clever things, and we want to be able to enable that. What we came up with is a tool called Colmena, and you can see some other talks about this on my YouTube channel, that describe our tool, which allows you to express these complex policies for how to steer computations into a series of simple agents that work together to form a complex policy. That active learning example I talked about earlier, you could express as a series of 6 agents, each with a simple job like, given the queue that's been prioritized of which calculations to run the most promising one as soon as resources are available, but no earlier. Simple policy to write, yet can be combined with many other ones like this machine learning scorer, that as soon as a new machine learning model has been trained, reevaluates all of the possible calculations, or at least submits a calculation to infer their outcomes, such that we can later use that data to reprioritize the list. And by writing these as simple agents, you can still express complicated policies. Here you're showing the outcome of that type of agent deployed on 1,000 nodes of the Theta supercomputer at Argonne. Color shows what type of calculation that's being run. Shade indicates whether the node is actually doing work or getting set up to perform it. And you can see that over time we can have some interesting policies, like in the beginning, I don't have any information about which calculation to run next. So I'm going to run the inference to determine which are good as quickly as possible by devoting as much resources to them as available. Immediately thereafter, I'm going to run simulations spending no resources on machine learning because I don't have any new data yet. But once that data comes in, I can retrain the machine learning model, then rerun the inference on as many nodes as possible so that I can get to that next best decision as soon as possible. And by combining these together in intricate ways, you can utilize your resources more effectively. Here you're showing the number of good molecules that our algorithm has found after a certain amount of computing time spent. And you can see that after 6 hours, I find about 20% better materials using this complicated algorithm. We call it Update 8. And that's about 20% better than if we had used machine learning but not bothered to update the machine learning models, and at least a factor of 100 better than if we had not used machine learning to begin with. So, in short, by creating a system that could put AI right into that computational workflow, we can drastically shorten our time to finding the scientific outcomes that we need. Now, I haven't said much about how we implemented Colmena, just to talk about that briefly. Colmena is a Python library. It lets you express those different agents using as Python functions that communicate to the supercomputer or whatever computational resources you're using a queue-based model. So you can write streams of tasks to be executed and receive streams of results coming back from them. And Colmena's key work is really only over in this scheduling end. Everything else on how to take those tasks and execute them on supercomputers effectively is implemented by some existing toolkits. We didn't write our own. We used tools like Parcel to solve those problems since they're already very well studied within the computer science community. And with this tool, we've been able to build some more complex algorithms since this example that I've been talking about since 2021. We've extended that active learning pipeline to be able to do multi-objective searches where we try to evaluate multiple materials properties using a suite of calculations at multiple levels of fidelity, using more complicated machine learning models, and by tying multiple types of computational codes together, each with accuracy versus runtime trade-offs. And we've done this in such a way that can hide away as much of the kind of inner workings of how to execute on a supercomputer behind a Python interface where you simply write the type of search you want to run and then invoke a command line tool to execute that for you. That's called XML. There are a couple examples that you can see here on GitHub of the work that I'm actively pursuing actually this month. So with that said, one thing I mentioned during my talk at the Schmidt Institute, or the Data Science Institute, since we had so many intelligent people, I very much challenged them to tell me if they thought I was doing something bad. That if they heard the names of the algorithms that I was using and thought they weren't the best, could come talk to me, because indeed, the algorithms are not my expertise. And I'm always happy to work with people who have a stronger background than I do in a different subject. So this molecule design is one of those examples where I'm working with people with different backgrounds. I've also been working from a team out of the University of Illinois at Chicago and Urbana-Champaign on designing MOFs. My colleagues there, two very talented grad students, one of which who recently, or is graduating soon, congrats to him, created this diffusion model that creates the linkers that form the backbone of a metal-organic framework. They're the organic part. And I've tied that to the workflows that take those linkers, use them to create MOFs, and then evaluate whether those MOFs are good for something like gas storage. And because we can tie these workflows together with artificial intelligence, we've done it in a way that continually improves that linker with, or that diffusion model with more data based on the MOFs coming out of the pipeline, and continually improves the models that we use to screen through, deciding what the best calculations to perform are. And because we're doing this with Colbena, we're trying to do it all at the same time. We've also had some work on creating tools that do protein design. Here has a very similar tune. I have machine learning models that generate proteins. These are built on large language models. I think they're GPT based, but I'll defer to my paper from, or the paper from my colleague Gotham that describes how they function. But the key point here, at least for this talk, is this is yet another example of how we can take a scientist's view on, if they had the ability, how they would integrate intelligence into their workflow and implement it in a way that uses many computational resources together all at one time to be able to solve a scientific challenge more rapidly. So to summarize, the ideas that we've been pursuing are one of the ways that I think AI can really change how we do computational science, is to move away, or continue moving away, from doing brute force searches to be able to solve a problem, to one where we combine together AI and simulation together into a single application that integrates them very closely, such that we can really get the maximum out of both the computational loop and the machine learning models. So with that said, one of the other kind of ideas that this notion of integrating AI into a workflow brings forward, at least for me, is that we're no longer treating this AI model, which is at its heart an empirical model of the same time that we use in many other areas of science, as a rapidly evolving entity. And that's perhaps different than how empirical models are conventionally used. One paper that I read a lot during my master's degree in 2011 was a paper from 2004 that contained the interaction parameters for how many different metals interact and form alloys. Now, this is a great paper, and in the past 20 years, one could take a criticism in that this table could probably have better numbers in it. We've improved our ability to fit to scientific data. There's certainly been more data coming out about these kind of materials, yet this paper has been and will remain static. And another kind of idea that I've been thinking about is, how could we change computational science if all of our models were to be allowed to change? And as I'm thinking about that, I realize it's a little problematic. There are many concepts for being able to develop algorithms that rely on a changeable machine learning model, such as taking a existing algorithm like molecular dynamics and learning subroutines in it, such that they can switch back from being a machine learning model to perhaps a more accurate one over the course of time. And there's some interesting papers you can read about this from around 2015. And further, there are algorithms that are built around the core concept, like active learning, that we can update this machine learning model frequently. There's work on how to do optimizations while simultaneously fitting a machine learning model, or how to use a evolving unsupervised learning model to direct an ensemble of simulations to less explored regions of configuration space in the case of proteins. And while these ideas, of course, have been around for a while, 2015 was not the first publication thinking that we could do this kind of on-the-fly learning. We still haven't seen many of these types of computations yet. And there are some real challenges behind this. The first of which is that the ways we might want to tie them together, these kind of flowcharts, are intricate, and expressing those intricacies is problematic, or at least challenging. And that we've illustrated some of the ideas around with Colmena. But there are many more problems other than it's hard to do. The second is that keeping track of those machine learning models is another route for tediousness. Being able to ensure reproducibility given a model that changes frequently is not how we're used to doing things in science. And then secondly, these machine learning models are by their nature unreliable. We shouldn't trust them in regions that they don't work very well. And there are many subtle shades to how to trust a machine learning model and then be able to use that trust to decide how it should be integrated into a larger workflow. And we'll talk about these two ideas in a little more detail. And the first of which, around sharing models, one of the projects that I want to bring your attention to is work that we are spinning up at the University of Chicago and others on how to create software infrastructure that makes training these machine learning models easier. Or sorry, not training them easier, but sharing them more easily with others. What they're creating is a toolkit that will allow you to publish your machine learning model up to a resource that will then allow others to use it as simply as calling any other Python API. I could say, give the name of your model and then invoke it in Python without having to worry about downloading any files or reading any papers or installing any software from GitHub. It's just an API that you can invoke. And since this is being designed for scientists, it's linked with all of your publications and data sets and your GitHubs, so that this isn't just a black box model for people. They can gradually pull back the layers to understand how it works and perhaps how to make it better. So that's Garden. I encourage you to check out this project and to engage with that team, because we're still in the process of being able to learn how to make a tool that's as useful to scientists as possible. The other problem that I alluded to was that building an application that relies on an ever-evolving model with uncertain provenance is difficult because we don't know when to trust it. And that's not the kind of interface that we really want for being able to use a subroutine. I just want to have a contract that I can give to the computer to say, produce an answer within a certain bound and have the algorithm work it out for me. And now the complicated part of that is once we start changing, what does find acceptable mean? That can mean a lot of different problems, and ensuring that those assurances are met requires some clever thinking. The answer for what the person could mean could be anything as simple as, when I call that function, I want the answer to be within a threshold. But that function can often be buried inside of a larger calculation, and I might want to know, well, I don't really care about that function call, but I want to ensure that my partial differential equation that I'm solving can be evaluated such that its outcome is within a tolerance, that I can say follow the trajectory and get to the same point whether I use that machine learning model or not. Or it could be that I care about that the property of that end state, not the actual coordinates, but a derived value from them, is the same, and this goes on. And all of these problems are complicated because we don't actually have a statistic that tells us the answer to any of these. What we have from a machine learning model usually is some metric of 0 means I'm perfectly confident in this, and a very large number means I'm very uncertain. And that sometimes correlates with the accuracy of the outcome of that single call, and sometimes it doesn't. So what we've been exploring around the University of Chicago, and particularly one of my former students, Yuli, now at NVIDIA, had it developed, is an algorithm that uses a controller to help ensure we can take that lossy metric about how good a machine learning model is, like how far is the new point from something we've seen in our training set, and turn that into a cog in a reliable machine that will ensure our requests are always met. So what she did is she took a simple way of integrating a machine learning model. A simple thing is my new point close enough to a training set? If yes, use a surrogate model. If not, use the original. And tied that to a controller such that we could change the threshold of when we will run a machine learning model or not, based on feedback for how well that machine learning model has been performing. And in this way, we can ensure that our requests that say our energy is never off by more than 2 millielectron volts, and get that answer with the maximum speed up as possible. So this is just one answer. It certainly doesn't provide all of the things that we need in order to use a unreliable model effectively in a complicated algorithm, but starts moving us down this road. And some of the ideas we're exploring, and I'd be happy to talk about, include, is there a better UQ metric for how I should measure whether that model is reliable other than just the distance from a point in the training set? Or if I'm running many copies of this surrogate function, how do I make it such that they all share the same information together when deciding whether to use that surrogate or not? Do I care about retraining this machine learning model and it forgetting the original data it was trained on? Or, as we'll talk about in just a few minutes, what if I made it such that yes or no weren't the only answers to use surrogate or not? So with that said, that wraps up really what I had to say today on how to develop machine learning models that are treated as evolving and uncertain objects, that will hopefully move the community more from the idea that once a model based on data is created, it should remain static for the sakes of scientific reproducibility, to something that can be treated as a versioned object that's always available for being changed, and then integrated into an application that is aware that this machine learning model is not always trustworthy and that it can change over time. And one way we've explored doing that is to use controllers to help ensure that that machine learning model is used appropriately. So with that said, as I've indicated on the last slide, there are one other concern that I've been thinking a lot about, which is instead of treating computation as I should run with the best accuracy I can given a computational cost budget, that I should instead be prepared to run many different types of fidelity. And this, for me, kind of boils down to one way of thinking that I've had for a while and have started to revisit. And this illustrated by a good graphic from a very interesting paper, so my apologies for altering their figure, illustrated one idea of machine learning is that we could say achieve accuracy goals that we had for conventional physics-based approaches at speeds just as good as the unreliable classical models that are typically available for many types of computations. And I don't think this is possible. I don't think we'll be able to recreate a surrogate as good as the code we're trying to replace, and we're certainly not going to create machine learning models that are as fast as simple classical empirical models. There's not a machine learning model I've made that I could fit in a main body of a scientific manuscript. All of them are far more complicated, so the computational cost will probably remain higher. But instead, if we think about the fact that we'll never achieve these endpoints, we could envision instead that machine learning models give us many different ways of bridging the gap between these two. And as we'll discuss towards the end of this section, that could allow us to do many impactful things in improving computational science. And as I alluded to, there's not just one way of being able to build this bridge between classical and physics, but, here, so the words classical correspond to this figure being from a quantum mechanics describing paper, where classical describes models that don't assume quantum systems, cheap but poor. Quantum refers to the full quantum mechanical treatment, which is accurate but expensive. Sorry, I should have mentioned that earlier, not knowing what background you're coming from. So just to recap, now that I've had that parenthetical, we're going to talk about the ways we can have a trade-off between those example ends of a spectrum. The first of which is the most common, that you can bypass that computation completely. And we've done a lot of work like this at Argonne, where it follows a similar theme of run that target computation many times. In this particular paper, we ran solvation energy calculations with a quantum mechanical method about 500,000 times, trained a machine learning model that emulates the parts of the physics we want. I want to be able to go from the molecule structure and the name of the solvent that I'm running to the solvation energy. So I do that using a message passing network, which takes the molecular structure and is a graph, and produces a function that I can vary both the structure of the molecule and the properties of the solvent, and be able to predict with reliable accuracy what the solvation energy will be. And this is one way. It gives me 1 point on that spectrum between perfect and cheap. Another way I could do it is to say use a approximate method or a cheaper version of that physics function as an input to a machine learning model. Often in the world of chemistry, this is called delta learning, based on some papers by Matthias Rupp in the early 2010s. And it follows a general theme that instead of training directly on your output function or using transfer learning to create a function that takes only the inputs to that calculation and produces an estimate of its outcome, we could instead use a cheaper physics model. Like, instead of computing a wave function method like G4MP2, we can do cheap DFT as an input, and then learn the difference between the two using machine learning. And as shown in a paper we did in 2019, this can give you about a 30 to 40x, or sorry, a 3 to 5x increase in accuracy and in a greater computational cost. And so I have to perform this calculation first, which may be 100 times faster than the wave function method, but is still 1,000 times slower than machine learning, as an example. So in short, this gives you a second point on your curve. You could also imagine more not by computing the same property the same way, but with a cheaper method. You could think about cutting corners on how you compute a property. For example, if I'm going after computing the ionization potential of a molecule, how much energy a molecule gains when I charge it. Instead of doing it precisely, where I do the full steps of the calculation, I induce the charge, and then I let the molecule's geometry change in response to being charged, I can instead use the vertical potential. I can only do one of the two steps. And this gives me a second step between being able to start from, say, nothing, or run a cheaper version of the calculation, or in its entirety. I can say, have a machine learning model that gives me multiple steps along that approach, further building in that bridge. So here, this result I'm showing you are the outcomes of machine learning models prediction, its performance accuracy under 3 conditions. Level 0, I give only the geometry, or I give no information. I give a guess for what this geometry is. Level 1, I compute the vertical ionization potential. Level 2, I compute this one, but I neglect the solvent. And you can see it gives me gradually better accuracy. Full details are here. Or you can think even more creatively, and instead of computing what the actual outcome of your calculation is, you can compute something that's related but cheaper. And a paper I really like for this came out in 2014, where instead of computing the melting temperature, very expensive, they computed the bulk modulus, which is related to melting. Materials that are stiff typically melt at high temperatures, and use the outcome of that bulk modulus calculation to predict melting temperature. And you can see here by doing that adjacent property, they decrease the error of their model by about, looks like a third, by computing a nearby property and feeding that as input into machine learning. So here they show what happens if I go purely from the original inputs to the problem, the crystal structure, to predict the melting temperature, error about 350, to instead computing some adjacent properties, using those as inputs to the model, cuts it down to about 260. So another way of being able to fill in those potential alternatives you could have to doing either nothing or doing everything. You could also perhaps change the algorithm where I'm still trying to do the correct calculation and I'm doing it at the correct level of accuracy, but I've changed how in order to make that algorithm approximate. So here, one example is work that I'm doing with some colleagues at the University of Chicago and Argonne on trying to compute the vibrational properties of molecules easily. Now, in order to do that, we're computing the second derivatives of the energy of the molecule with respect to the atomic positions. And if I were to do that accurately, let's say I only have 2 degrees of freedom in my molecule, I'd have 9 calculations. I'd have to do one direction, I'd have to do the other direction, then I'd have to do both together. Now, one way of cutting corners is by making approximations about what these coordinates could be. Like, let's say I thought they were the same, or that x and y actually describe the same thing. I can cut down from 9 to 3. If I assume that the point I'm evaluating is at the bottom of a local minimum, then that means I can approximate that forward and backwards on either side of that minimum are the same, and that cuts me down from 3 to 2. So in this way, I'm showing how I'm cutting corners using my intelligence about what I think the problem is or my assumptions. But that's costing human effort, and there are parts where I either can't spend the effort because this calculation needs to run quickly without my input, or I don't know enough about it. So in that case, we tried out using machine learning to be able to figure out which corners to cut. And we did that by, say, instead of by training a machine learning model, which enabled us to kind of gather data about each of these different variables, degrees of freedom, concurrently. I could say pick a point that mixed both of them, and then use a technique like compressed sensing in a machine learning model to find which of those degrees of freedom, shown in this part. Color means that degree of freedom is important, white means it doesn't. And I can use compressed sensing to find out which ones those are quickly, thereby finding a fewer number of parameters, requiring less data. Or I could say that these degrees of freedoms are actually related to each other and use a machine learning model that learns a reduced representation. Instead of treating all of these degrees of freedom as independent, I could learn an underlying model that expresses the relationship between x in one direction for one atom and x in a different atom. Their interatomic force fields, we can describe how both of those atoms are actually the same, or at least close to each other, and thereby further reduce the amount of data that we need. And here, at least in one test case that we've had, we cut the amount of computational costs needed to compute one vibrational property called the 0-point energy by about a factor of 4 if, we only needed it to an accuracy of 1 kcal. Instead of doing 2,700 calculations, we could do 500, and that dramatically speeds things up. So with that said, if we had all of these different ways of expressing a bridge between perfect and easy, we could design AI algorithms like we're doing in XML that pick which level of calculation and trades off between expensive, doing them sparingly, and cheap, doing them all the time. I could say use my Proxima model set controller to not pick if, but how much machine learning to use. I could rethink algorithms, or I could say employ a GPT-based model to tell me what I could do instead and try that instead of computing the actual property I want. I could have said, like in that melting temperature example, pick a related property and evaluate that one instead. So with that said, that wraps up my conversation for today. What I want you to take away from this presentation is that there are a few different ways of thinking that at least I grew up having as a way of approaching computational science and reevaluate them now that we have all of these great AI functionalities. We could say replace the idea that we should do brute force searches when in doubt to ensuring instead that we increment artificial intelligence as closely into those computational workflows as we can. Or instead of treating a empirical model as static, we could make it reliable by perhaps using a controller to tell us when we should use it or reevaluate it or retrain it. Or instead, we could build some data infrastructure that ensures those machine learning models that I create can be used easily by others and changed by them and reshared, such that they're really evolving objects instead of something that stays in a paper for 20 years. And then finally, instead of thinking of it either being machine learning or else, we could really evaluate the many different ways that you can have trade-offs between a machine learning algorithm, such as by either reevaluating how we approach a problem or by training a machine learning model to go between our target method and something that's very cheap by employing machine learning that uses intermediate data from perhaps computing the calculation with different approximations or picking something related to it. So with that said, that wraps up my talk for today. The one thing that this presentation isn't complete without is pointing out that I'm just the tip of the iceberg on explaining all of this work. All of the things that I've described today are the product of many happy years of continuing to collaborate with people ranging from computational chemists to computer scientists to web developers, all of us together being able to come up with new ideas on how we can change computational science. So that wraps it up today. Feel free to leave questions in the comments if there are any topics you want to dig in further. But thanks for taking the time to listen through this. And I hope you're having a good day.